Hello everyone, this is George Kamiti. Welcome back to our channel. Today we are analyzing the Poisson's ratio as well as the three moduli of elasticity. Remember, we usually have three moduli of elasticity. That is the modulus of rigidity, the bulk modulus of elasticity, as well as the Young's modulus of elasticity. So we got a question here that's asking us to determine the Poisson's ratio and the three moduli of elasticity. Now join me as we solve the problem that we got here. And it says the following data relate to a bar subjected to a tensile test. The diameter of the bar 30 millimeters. The tensile load subjected on that bar 54 kilonewtons. The gauge length of that bar 300 millimeters. The extension of the bar due to this tensile load of 54 kilonewtons is 0.112 millimeters. Change in diameter 0.00366 millimeters. Determine or calculate the Poisson's ratio and the values of the three moduli. And the three moduli we are talking about are the Young's modulus of elasticity, which is denoted by E, the modulus of rigidity, as well as the bulk modulus of elasticity. Now, beginning with the Poisson's ratio. Now, we know that Poisson's ratio is usually given by the lateral strain divided by the linear strain. The Poisson's ratio is usually denoted by this symbol mu, and it is usually given by, or it is also denoted by 1 over m, where m is a constant that is different for different given materials. So when you get the Poisson's ratio, then you find its reciprocal that usually gives you the constant m. So this 1 over m, which is mu, the Poisson's ratio, will be given by the lateral strain divided by the linear strain. The lateral strain is given by the ratio of change in diameter divided by the original diameter of the bar. Remember, we said this: when a bar is subjected, or when a material is subjected to a tensile load, there are two things that will happen to this bar. One, the bar will extend, it will increase in length, and at the same time, its thickness will reduce. So we are going to have an increase in length, but at the same time, a decrease in diameter, or a decrease in thickness. So this decrease in diameter is what we call lateral strain, whereas the change, the increase in length, is what we call the linear strain. That is, the strain as a result of that increase is the linear strain. The strain as a result of this decrease in diameter is the lateral strain. The linear strain, on the other hand, is usually given by change in length divided by the original length of the bar. Now let's begin with determining the lateral strain. And we are going to have lateral strain is equal to change in diameter. We got it here, 0.00366 millimeters divided by the diameter of the bar, 30 millimeters. So divide that by 30, and this is going to give us 1.22 times 10 raised to the power of -4. No units, because that is the ratio. Linear strain, on the other hand, will be equal to the change in length, the extension of the bar, 0.1 112 millimeters. The length of the bar, that is the gauge length, 300 millimeters. So we divide this by 300 millimeters, and this is going to give us a strain of 3.733 times 10 raised to the power of -4. The Poisson's ratio will now be given by the lateral strain, which is 1.22 times 10 raised to the power of -4. Divide this by the linear strain, which is 3.733 times 10 raised to the power of -4. And this is going to give us a Poisson's ratio, or 1/m, being equal to 0.327. So that is the Poisson's ratio. So we have answered part 1 of this question. Part 1 of the question. Part 2 of the question is asking us to determine the 3 moduli. Now, starting with the Young's modulus of elasticity. The Young's modulus of elasticity. That is E. Young's modulus of elasticity. The Young's modulus of elasticity is given by the ratio of stress to linear strain. And stress is given by load divided by cross-sectional area. We got a load of 54 kilonewtons, so what we are required to determine is the cross-sectional area of this bar. And since it is circular, because we have the diameter, the cross-sectional area of this bar will be given by pi/4 multiplied by the square of its diameter. And this is going to be pi/4 times. The diameter of the bar is 30 millimeters. We have to convert that to meters. 1 meter is equivalent to 1,000 millimeters. Therefore, 30 divided by 1,000, that happens to be 0.03 squared. And that's going to give us a cross-sectional area of 7.068 times 10 raised to the power of -4 square meters. So that is the cross-sectional area of this bar. Now we can be able to get the stress, and the stress will give us or will be equal to the load 54 kilonewtons divided by the cross-sectional area, which is 7.068 times 10 raised to the power of -4. And this is going to give us a stress of 76,394.37 kilonewtons per square meter. So that is the stress in this bar. This stress is in kilonewtons per square meter, but we can still convert it to meganewtons per square meter by just dividing it by 1,000. So when you divide it by 1,000, we are going to have 76.39 meganewtons per square meter. Now we can get our Young's modulus of elasticity by taking our stress. We have said we convert it to meganewtons per square meter. That is going to be 76.39 meganewtons per square meter. Divide this by the linear strain, and in this case the linear strain is 3.733 times 10 raised to the power of -4. And that is going to give us a Young's modulus of elasticity of 204,634.34 meganewtons per square meter. You can write this in standard form. This is going to be 2.046 times 10 raised to the power of 5 meganewtons per square meter. So this is the Young's modulus of elasticity. Then from there we go to the modulus of rigidity. So modulus of rigidity. The modulus of rigidity, let's do it on this space. For us to get the modulus of rigidity, we are going to use the relation, the formula of the relation between the Young's modulus of elasticity and the modulus of rigidity. And the relation between the Young's modulus of elasticity to that of the modulus of rigidity is given by E is equal to 2G. G is the modulus of rigidity into 1 plus 1 over m, and in this case 1 over m is the Poisson's ratio, which we got it here, the Poisson's ratio. Young's modulus of elasticity, 204,634.34 is equals to 2G into 1 plus the that is the Poisson's ratio, 0.327. So 1 plus 0.327. So this will be 204,634.34, which will be equal to 1 plus 0.327 is 1.327. 2 times 1.327, that happens to be 2.654. 2.654 G. 2.654 G. Now to get the value of G, we are going to divide both sides by 2.654. Divide this side again by 2.654. And that is going to give us G, that is the modulus of rigidity, being equal to 77,104.122 meganewtons per square meter. So that is the modulus of rigidity. You can also write it in standard form, that is times 10 raised to the power of 5. It's not a mass, but when we do so, we are going to have G is equals 0.77 times 10 raised to the power of 5 meganewtons per square meter. So we are done with the modulus of rigidity. Finally, we are going to determine the bulk modulus of elasticity. The bulk modulus of elasticity. We are going to use the relation between that is the formula that gives us the relation between the Young's modulus of elasticity and the bulk modulus of elasticity. And their relation is usually Young's modulus of elasticity is equals to 3 times the bulk modulus into 1 minus 2 over m. 2 over m. And remember, this 2 over m can be rewritten as 2 times 1 over m, whereby 1 over m is the Poisson's ratio. So we are going to have Young's modulus of elasticity, which is 204,634.34 being equal to 3K into 1 minus 2 times the Poisson's ratio, which is 0.327. So this is going to be 204,634.34 being equal to 3K into 1 minus 2 times 0.327 happens to be 0.654. So this one will lead us to 204,634.34 being equal to 1 minus 0.654, that is 0.346. 0.346. 3 times 0.346, that is 1.038K. 0.038K. To get the value of K, we are going to divide both sides by 1.038. Divide this side as well by 1.038. And when we do so, we are going to have K, the bulk modulus of elasticity, being equal to 197,142.91 meganewtons per square meter. When you write it in standard form, that is times 10 raised to the power of 5, the bulk modulus will be given by 1.97 times 10 raised to the power of 5 meganewtons per square meter. And that's how we go about it. So we have determined the Poisson's ratio and the 3 moduli, that is the Young's modulus of elasticity, which is there, the modulus of rigidity, as well as the bulk modulus. So ladies and gentlemen, please, if you haven't subscribed to this channel, hit that subscription button and we are going to appreciate so very much. Let's meet in yet another lesson. Thank you. This is George Kamiti.